Okay, let's get talking about variation. Right, so for each equation, determine whether it shows a direct variation. If it does, find the constant variation and write it in simplest form. Okay, so for these, you're going to solve for y. That's just all you're going to do. So we've got negative 2x plus 5y is 0. So 5y is 2x and y is 2/5 x. Now, if the y-intercept over here is 0, if it's just, there's just nothing there, then the correct answer is yes, we've got direct variation. And the k value, called the constant of variation, that's just the slope. Okay, so we get that. That's how it works. Now, what if, let's make up a new one here. Let's say plus 7. Okay, so for part B, we're gonna do a little different problem here, just to kind of spice it up a little. So we'll say negative 4y is negative 5x plus 7. I know my 5s look like s's, but you can tell what it is by the context. So I divide both sides by 4. Okay, and then I say, all right, do I have a non-zero y-intercept there? If I do, which in this case I do, then it's nope, no direct variation. Okay, and therefore I don't even worry about the constant of variation because it's not a variation situation, so there wouldn't be a constant of variation. Okay, the reason why this one does not represent direct variation is because of this extra number here. All right, so y, the value of y, is not directly dependent on the value of x and the constant of variation. There's this extra pesky number over here going on. Okay, it'd be kind of like saying, maybe I'll type a little, kind of like saying, hey, I'm going to make a long distance phone call. And that long distance phone call is, let me do a dollar sign here, is 35 cents per minute. Cool. That's direct variation. Okay, because the cost, or y, is completely dependent on one thing: how many minutes. Okay, compare that with, hey, I'm going to make a long distance phone call and it's 35 cents per minute. Plus a $2 connection fee. All right. Now that is not direct variation because the cost, the y, is not completely dependent on the number of minutes. There's this extra pesky guy over here. Okay. If we write these things as regular equations, the first one would be y equals 0.35x, and the second would be y equals 0.35x plus 2. And so you have a non-zero y-intercept that's helping to determine what your y value will be. So that's what's going on. Okay, so now once again we're determining, do we have direct variation or not? Okay. But we're not given an equation, so that's kind of stinky. Now, direct variation, anytime you've got direct variation going on, you are using the formula y equals kx, where k is the constant of variation. And there's no plus, any y-intercept or anything like we just talked about. Okay. Therefore, whenever we are talking about direct variation, we're using this equation, then we could divide both sides of the equation by x and say, hey, the constant of variation in a direct variation scenario is always y divided by x. Okay, so if your y divided by x is always the same thing, if it's always the same thing, then it's always satisfying the direct variation equation. So you have direct variation. So let's figure that out real quick. Okay, so let's do y divided by x, and that'll be 1/4. And I'm going to grab my calculator here. And then 1.5 divided by 6 is also 1/4. And 1.75 divided by 7 is also 1/4. So because that number is constant, it is direct variation. If any of these numbers were different from any of the others, I would have chosen that and said, nope, this is not direct variation. Something else is going on. Okay. I'm going to put an 8 right there. So instead of -10, it's -8. All right, so let's do the same thing for the second one. So I'll just write it over here. So y over x. So 4 over -10, that's -0.4. -2 over 5, and that's why I'm doing the y divided by the x, is -0.4. And -8 divided by 25 is -0.32. Uh-oh, one of them's different. So, our y over x's are not constant. So we don't have a constant of variation based on the direct variation equation. Therefore, not direct variation. Okay, so now we're going to build the direct variation equation, and it's not too bad. Okay, so it says, suppose that y varies directly. Oh, I gotta click on this thing. Varies directly with x. Okay, so I see varies directly. So immediately I'm thinking y equals k times x. There are other basic templates for other types of variation, which we will see soon enough, but not in this video. All right, so then it says, all right, well, when y is 8, x just so happens to be 20. Oh, that's nice. Okay, so presumably we're supposed to solve for k, so we do. And we get k is 0.4. All right. So that tells us that our direct variation equation for this scenario, whatever's going on, is y equals 0.4x. Just taking the 0.4, k equals 0.4, and plugging it in for k and writing it right there. Okay, so this is our direct variation equation. It represents whatever scenario, whatever situation is being discussed over here. So they say, all right, you've built this tool, this direct variation equation, now go use it. Okay, so this is our answer to part A. Part B says, well, hey, when x is 7, what does y happen to be? Well, that would be 2.8. Okay, 0.4 times 7 is 2.8. Okay, so they say go out and build the equation and then go use it. And it gets pretty routine pretty quick. Okay, let's do a word problem. It's going to be really similar to the last one, except now there's a story, so it's more interesting. Okay, on a given planet, the weight of an object varies directly with the mass of the object. Aha, sentence number 1, varies directly with. Okay, so I see direct variation, so immediately I'm thinking the y equals kx formula. All right, now let me give you a little hint here to make things a little easier. Whatever comes before this underlined statement of varies directly with, whatever comes before it, that's going to be your y. Okay, and when I say whatever comes before it, I mean whatever quantity that can take on different values. Well, weight would be that guy. That's going to be our y. And whatever comes after the underlined portion, mass, that's going to be our x. And you can leave it y and x if you want, but I'll do w and m, just if I want to. All right, so suppose that an object whose mass is 3 kilograms, and again, 1 kilogram, that's on Earth's surface, that's about 2.2 pounds. So a little over 2 pounds. So suppose an object whose mass is 3. Okay, so let's plug 3 in for our mass variable. Weighs 18 newtons. So we'll plug in 18 for our weight variable. And then we'll solve for k. And then we can now take this guy and replace K with 6. 6 newtons per kilogram is what it actually is. Okay. All right. So that's that. Now we haven't actually answered the question, but we've done a lot of the work. We've done half of the work to get there, maybe more. So then it says, calculate the mass of an object that weighs 12 newtons. Okay. So it weighs 12. Aha. So 12 gets plugged in for weight. And we want to solve for mass. So we divide by 6 and we get 2 kilograms. I know it's kilograms because the last time they talked about mass, it was kilograms. Okay. And then that's how you do it. So it's just like that last problem, except now there's a story, which makes it cooler and more interesting. Plus, because of the context of the story, sometimes you might be able to say, wait, that doesn't make sense. You know, the answer I got, I need to rework it. Like, what if I had gotten negative 2 kilograms? That would not make sense. Mass is not negative. Okay, David's riding a bike. The distance he travels varies directly with the number of revolutions his wheels make. I see that and I say, y equals kx. I'm going to need that at some point, probably. Okay. All righty. So let's think about what's going on here. So they say that the distance that he travels varies directly with how many revolutions of the wheels. So number of revolutions of the wheels completely determines the distance traveled because it's direct variation. There are no other factors. Okay, so let's see if I can draw a bicycle here. I'm not very good at it, as you can tell. There's the banana seat or whatever. Okay, actually, that actually looks like a bike enough. So let's just to get familiar with the problem. Let's say that he's got a standard 26-inch wheel. Okay. So what would be the distance around? That'd be the circumference, which is pi times diameter. And so pi times 26 inches is about 81 inches, which is about 6.8 feet. Okay. So every time his wheel, so every time the part touching the road comes back around, he's gone just about 7 feet. Okay. So that's kind of what's going on. So that's what they mean by a number of revolutions. How many times has the wheel gone all the way around? Okay. Well, let's take a look at what what we're supposed to here. So part A, how many revolutions does David make per foot of distance traveled? Now remember, per anywhere in the world means divide. Okay, so revolutions divided by feet, distance, okay, measured in feet. So that's what we got going on here. Right. And so, well, we know that, let's see, when he's gone 2 revolutions, he's gone 8 feet, right? All right, this says how many revolutions per foot? Okay, so number of revolutions divided by number of feet. So that would be 2 revolutions divided by 8 feet. Okay, so he has a much smaller wheel because we were going almost 7 feet in just 1 revolution. So 1/4. 1/4 what? Well, we did 2 revolutions per foot. So it'll be so you could say 0.25 revolutions per foot if you want. But anyway, 0.25, 1/4, that's our guy. Okay. Part B, what is the slope of the graph? Well, I don't know. I guess we could work on that, I suppose. Let's do a different color here. What is the slope? Well, we've got this point of 0, 0, and this point of 2, 8. So we're going to rise 8 and we're going to run 2, which is 4, which is just what we got over here flipped over. Okay, now that answers the whole question, but in order to understand how it relates a little more directly to what we've been studying regarding direct variation, we might say, hey, let's build a direct variation equation. Okay. Well, we know that the slope is 4 and the y-intercept is 0. So it's just y equals 4x, where 4 is the constant of variation. And that's that. And because they said it's direct variation, because they said that, we knew, or well, that told us right off the bat that the line representing the situation had to go through the origin, so that there would be a y-intercept of 0. So that, yeah, so you would actually have direct variation.